Since we've now been formally introduced to the idea of a linear combination of vectors, I would like to consider the following example. If possible, I would like to write the vector v, -1, 7, 2, as a linear combination of vector u1, which is 1, 3, 5, u2, which is 2, -1, 3, and u3, which is -3, 2, -4. So first thing I'd like to do is set up what a linear combination of these three vectors would look like. So c1 times u1 plus c2 times u2 plus c3 times u3, that's going to be equal to the vector v. Now our goal is to, if possible, solve for c1, c2, and c3, or prove that no such values exist. So first thing I'd like to do is write out what the full linear combination would look like. So c1 times the vector 1, 3, 5 plus c2 times the vector 2, -1, 3 plus c3 times the vector u3 -3, 2, -4. That's going to be equal to the vector -1, 7, 2. Now, in order to consolidate the vectors on the left-hand side to one single vector, I'm going to apply the definition of scalar multiplication. So I'll distribute the c1 through to each of the three terms. So c1, 3c1, 5c1, plus, for the second vector, 2c2, -c2, 3c2, and for the third vector, distributing the c3, that'll be -3c3, comma, 2c3, -4c3, and that is once again equal to the vector -1, 7, 2. Got a little short on room over there. Now, to combine these into one single vector, we'll add the corresponding components together, and we'll have one big happy vector. So, adding the first components together, that'll be c1 plus 2c2 minus 3c3 for the first component. For the second component, we'll add the corresponding second components together. That'll be 3c1 minus c2 plus 2c3. And then for the third components, we'll add the corresponding third components together. That'll be 5c1 plus 3c2 minus 4c3. And once again, this is supposed to be equal to -1, 7, 2. Now what we're going to do is turn this into a system of equations, three equations for the three components, and three variables for the three different vectors that we started with. So the corresponding first components need to be equal to one another. c1 plus 2c2 minus 3c3 is equal to -1. The second components will need to be equal to one another. That'll be 3c1 minus c2 plus 2c3 is equal to 7. And finally, for the third components, those will need to be equal as well. That is 5c1 plus 3c2 minus 4c3. That'll be equal to 2. Now, in order to solve this, I'm going to set up an augmented matrix and take it to reduced row echelon form. However, because we've already been through this process many times, I'm going to use my calculator to obtain reduced row echelon form. Now, there is a shortcut in this process that I would like to make everybody aware of. Technically, the first column represents the coefficients of c1, the second column represents the coefficients of c2, and the third column represents the coefficients of c3. Sorry, forgot how to write 3 for a second there. However, if you take a look back at the original problem, the columns of this matrix actually correspond to the vectors u1, u2, and u3. Vector u1 is 1, 3, 5. The first column is 1, 3, 5. Vector u2 is 2, -1, 3. That's the second column. And u3 is -3, 2, -4. You'll notice also that the augment, what it's equal to, is the vector for our linear combination. -1, 7, 2. -1, 7, 2. So the shortcut that you can use in the future for problems like these is the fact that the coefficients of the c1, c2, and c3 will be the same as the components of the vectors. Now we're going to take this down into reduced row echelon form, but we're going to use a graphing calculator in order to do so. So let's make sure that we have a graphing calculator handy and ready to go. And I'll do my best to make this as visible as possible. Oh boy, got stuff in there from last time. So I'm going to enter my matrix menu. Matrix menu on this calculator is obtained by pressing second followed by the inverse key. And this is the matrix menu. We're going to start by editing a matrix. So heading over to the edit column, I'm going to select matrix A. I don't care what was in there from last time, it's not important to me. What we have here first, the size is going to be a 3 by 4. So 3, enter, 4, enter. And then I'll be entering each row from left to right, and then we'll go down one row at a time. So 1, enter, 2, enter, -3, enter, -1, enter. Second row we have is 3, -1, 2, and oops, didn't press enter after the 2. So 2, enter, 7, enter. There we go. And then the third row we have 5, 3, -4, and 2. Now one great thing to always double check is, second quit, re-enter the matrix menu and select the matrix that you just inputted just to make sure that everything that's in the matrix here matches everything that's in the matrix here. After you've verified that everything is correct, re-enter the matrix menu, go to the math column, and arrow down or up until you have found RREF, which of course stands for Reduced Row Echelon Form. You'll notice that it opens a set of parentheses when you do so. As such, you'll need to actually select the given matrix. Second inverse to enter the matrix menu. Select matrix A, close your parentheses, and press enter. This is now interpretable in terms of a final answer. However, to make it a little bit more aesthetically pleasing, I'm going to press math, followed by enter, to convert those entries into fractions. So at this point I'm going to copy down what I see in terms of these fractions. The first row is 1, 0, 1/7, 0. The second row is 0, 1, -11/7, and 0. And the third row is 0, 0, 0, 1. Once we have that copied down, shut the calculator off, and let's give this a full interpretation. The first row is telling us that C1 plus 1/7 of C2, C3 is equal to 0. Second row tells us that C2 minus 11/7 C3 is equal to 0. And the last row tells us 0 equals 1. That last row is all that we need. We do not need the first two rows at all. All that we need is this interpretation, this 0 equals 1. What the math is telling us is, it is possible to write V as a linear combination of these three vectors, provided that 0 is equal to 1. Because 0 is equal to 1, what it's actually telling us is it's impossible to do the task assigned to us. So we'll say, therefore, V cannot be expressed as a linear combination of U1, U2, and U3. So the three possibilities that we get for this system, we got an inconsistent system, which means it's impossible. If we had gotten a consistent system, that would mean that there's exactly one way to do so, and the solution of the system would make itself present to us, or make itself, we would be aware of what the solution is. And finally, if it's a dependent system, that means that there is an infinite number of ways in order for us to express V as a linear combination of U1, U2, and U3. We would simply need to pick one of those.